All right, so we're somewhat familiar with the platform. I'm not going to go into too much detail about Exalogic in particular. What I really want to focus on is some of the optimization, some of the work that we did and the optimizations that we did around the Coherence products that were motivated by Exalogic, maybe driven by Exalogic. But I think what you'll see out of this presentation is that a lot of that work and a lot of the features and a lot of the investments that we made in the architectural changes targeted towards Exalogic are also going to benefit the core product running on any platforms. Right? This is kind of the standard disclaimer slide. Don't believe anything I'm about to tell you. All right. So since we're already very familiar with Exalogic, the hardware, I'm not going to spend too much time on this, but just a quick recap. And actually, I think this slide's a little bit dated now. I think this is Exalogic v2. I think that there's X3 just came out. But in v2, we have each compute node has 24 cores, 96 gigs of RAM. In a full rack, we have 30 compute nodes. We've got quad data rate InfiniBand, Fabric backing the rack, and on each compute node we have also flash-based storage. I think somewhere in the range of 100 gigs. Right. So there's kind of two aspects of the work that we did around Exalogic that I want to kind of focus on today. The first aspect is some of the work that we did to target optimizing the network performance for the Exalogic platform. The second part of the talk, I want to take a look at some of the things that we did around trying to take advantage of the flash storage. All right, so I mentioned that one of the things that we get with Exalogic is Infiniband. Right? So some basic stats or some basic information about Infiniband. Infiniband designed for extremely high throughput, low latency applications. Jumbo frames. We can move a lot of data in each packet, in each frame. There's support for standard IP stacks on Exalogic. On Infiniband. So we have IP over Infiniband. So we can, we have support out of the box for UDP, TCP. But in addition to that, we have a verbs-based API that we can talk directly to the Infiniband layer on. We also have what's known as RDMA, right? So remote direct memory access. Right? So we have the ability over Infiniband to register memory directly from the process space with the HCA, the Infiniband controller, and remotely write into that memory from another process. Right? And we'll see how later on we'll see how we're starting to take advantage of that ability and fold that back into kind of the networking stack and how we're looking at exchanging messages for coherence. Okay. So Infiniband as network transport, though it's designed for high throughput, low latency, jumbo frames, and out of the box it has some compatibility with standard IP stacks. Our first experiment with this is, well, okay, let's get one of these boxes, let's plug it in, let's push it, let's see with our legacy TCMP transport, right, our datagram based transport, let's see how much faster we can get. What we found was that though the network transport is designed for low latency, high throughput, what we found was that simply plugging it in didn't really give us the scale up that we wanted. Right? What we found was that in order to really take advantage of some of the capabilities of the actual underlying transport, we needed to kind of go back and re-examine, take a look at how the networking stack within Coherence is designed, both in terms of threading model and how it's folded into the product as a whole. Right? So that's kind of the walk that I want to take us through today, looking at how the networking stack evolved over time and some of the changes that we made in order to accommodate some of the benefits that we can get through Infiniband. All right. So it's a little bit of a confusing diagram here, but hopefully when I talk through it, it'll make a little bit of sense. What we're just showing here is at a high level what the request flow looks like in Coherence. Right? So I've got a client thread here that issues a request. Right? When that request goes on the wire, right, internally within Coherence, all of the messaging protocols are inherently asynchronous. Right? But when this thread puts a request on the wire, right, this thread is then held. Right? right? And we hold it on a data structure called a poll, right? Basically, this thread is now blocked, waiting for a response, a logical response to that message, right? So this message is sent across to the remote server, where it's then queued onto onto the remote service thread. That service thread processes the request, or maybe it hands it off to another thread to process the request. Right? Hands it off to a worker. The worker processes the request, sends the response back to the service thread running on the client member. The service thread gets the response, processes the response, notifies this poll to unblock the client thread. Right? So this is, at a high level, kind of the flow of request processing within Coherence. If we dive a little bit deeper and look at the datagram-based transport, right, we can expand the diagram a little bit. So again, we have the client thread issuing the request. The client thread's held in this poll, right, waiting for a logical response. Well, what happens to that message when we queue it? Well, what happens is we actually queue that to a component we call the publisher. Right? The publisher is basically there's a single publisher per member, and it's responsible for taking logical request messages from all of the servers, or in this case, any thread that wants to send a request, so including the client threads, are queuing messages to the publisher, and the publisher's sole responsibility is basically take those logical messages and put them on the wire, either through passing them to another component, the speaker, to bundle them, so on and so forth, or putting them on the wire directly. They go on the wire, go over the network. We've got a component on the remote side, which is analogous, right? Which is basically pulling packets off the wire, assembling them into logical messages. Those messages are then delivered to the service thread. The services are then either processing them directly, or they're passing them off to a worker. Right? That worker then sends a response, and it kind of goes through this flow again. When it gets back to the client, the service on the client receives the message from its network threads, and on processing that response, unblocks the client thread. So at a very high level, this is kind of how the legacy datagram-based transport works. Right? What you can see from this is that the legacy transport is designed to be extremely pipelined. Right? It was written with the idea of scaling out. Right? It was written with the idea of being able to process very, very high throughput of messages, okay, with extremely low contention. Right? What we found, in our experience, what we found is that this architecture has enabled us to easily max out gigabit Ethernet. Right? Now, what we found, though, is that while that architecture allows us to scale out very well, what it doesn't allow us to do particularly well is to scale up. Right? And if we take another view of this flow, what you can see is that if we take a higher level view here, what you can see is that all of the clients or servers that are sending messages, they're all kind of going over one logical channel, right? So all of the threads on a given coherence member that are sending requests are all being funneled through a single publisher, a single speaker, right? That's putting those messages on the wire. We're pulling them off the wire into, again, a single listener, a single receiver, spreading them over to the, processing those messages and sending them to the service thread to be processed again, and so on and so forth, right? So you can see that that pretty soon it becomes clear that the publisher, the speaker, the listener, the receiver, and even to some degree the service threads become bottlenecks, right? They become single points of bottleneck. Right? What we found over the years is that what this means really is that as hardware evolves and we move into, if we start moving in the direction of many low-powered cores, right? What this means is that it really kind of starts to inhibit our ability to scale up. It inhibits our ability to again, going back to what motivated all this, it inhibits our ability to take advantage of improvements in the network transport. It inhibits our ability to take full advantage of the Infiniband. Right? So again, just to review, fixed number of transport threads, the publisher, the speaker, the listener, the receiver, that are funneling all the messages for a given coherence service member, limiting our ability to scale up. Right? We've got basically 4 threads that all the messaging is going through. The service threads themselves become bottlenecks. Right? All those messages that are being received and passed off to the service thread. Well, the service thread, in many cases, all it's doing is taking the message and then passing it off to a worker. Right? But that again becomes a single point of bottleneck. Historically, we've been able to address this by running multiple nodes per machine. Right? You have a lot of cores. Right? If you have a lot of cores, we've got a fixed number of transport threads. We've got bottlenecks in the service thread. Well, you want to take advantage of those cores, run more JVMs. Right? But as we start scaling to machines with 24, 40, 48, many cores, this starts to become a management problem. In addition to that, the IP stack adds latency. Right? Having to go through the IP stack, or having to go through the operating system, all that adds latency, in addition to the latency that we get from all the context switching that's going on. Remember? Because we've got the client thread context switching to the publisher, context switching to the speaker. On the other side, again, the listener, context switching to the receiver, back to the service thread, back to the workers. So we've got a lot of context switching. And individually, it may not seem like very much, but when you look at the system as a flow from beginning to end, it actually adds up to be quite a bit. All right. So that's kind of where we came from, right? What we started to do probably about 2.5 years ago, what we started to do was to take a look at some of the, again, the hardware improvements, the direction that market was going in. We looked at the Exalogic platform in particular. We looked at Infiniband. We looked at ways that we wanted to take advantage of that. And what we did was we started thinking about introducing a new logical messaging layer. So terminology is a little bit confusing here, but what we did was we introduced what we call MessageBus, and you can think of MessageBus as basically a layer of APIs. It's basically an asynchronous binary messaging API. Right? That API has many different implementations, or we envision several different implementations of that. We've got TCP-based implementation, right, based on TCP sockets. We've got an RDMA implementation for Exalogic. We also have an SDP-based implementation for the supercluster as well. But all these implementations, again, are implementations of this logical MessageBus API. Right? This API is designed to solve some of the problems that we were running into with the legacy datagram-based transport. In particular, we designed it to scale both up and out. Right? So we want to be able to handle machines, we want to be able to handle architectures with many cores, and be able to scale to many different connections, right? And be able to spread that load now over many different cores. In designing this, we also kept in mind some of the tricks and some of the benefits of the InfiniBand transport that we have, and be able to take advantage of RDMA, right? And be able to use RDMA to now exchange messages with extremely low latency, high throughput. Some of those properties, the basic properties of InfiniBand that we want to now be able to take full advantage of. All right, so this is just a quick slide to kind of run through how the RDMA implementation of MessageBus works. So the basic idea here with RDMA is that, again, each process can register some block of memory with the network controller, with the HCA. Right? Now, over InfiniBand, if you register some memory with your controller, and I've registered some memory in my controller, if you pass me that address, now I can write directly into that address. By writing to that memory, I can write to that memory by skipping the kernel. Right? Skipping. There's no operating system kernel context switch. There's no network stack switch on my side, or on your side either. Right? I'm writing directly into that memory. Right. So the way that our RDMA-based implementation of MessageBus, the transport layer, works, is we've got kind of the sending side and the receiving side, right? And each side registers a block of memory, and publishes that block of memory to the remote side, the peer of the connection. Right? So the way that a sender would send a message is we've got a message that's locally allocated in the sender's memory. It knows about this ring buffer. This is pre-register memory. So we first write a header saying, hey, I've got a message to send. It's 1K, and it's this is the address, or here's a token to get it, right? And we write that little block of metadata here. Right? The process on this side picks that up and says, oh, I've got to read a 1K message from this token, from this address. Right? So it allocates local memory. It does an RDMA read. And again, these are extremely quick. I think 1 micro. Gene, do you know the numbers? Low, single microseconds. Yeah, single microseconds. So we've got that metadata. We know where the address is. We know how large it is. We allocate some memory for it. We go and reread that address again over RDMA, bypassing the kernel, bypassing the TCP stack, bypassing any of those network stacks, which again are gonna bypass a number of copies along the way. Right? So we read that memory directly over RDMA into our local memory. And then using RDMA again, we write a receipt, basically saying, hey, I've got it. You can clean it up now. The other thing we did with MessageBus is we introduced the idea of having a separate MessageBus per service. Right? So rather than, if we go back to the legacy implementation, the datagram-based transport, on a single coherence member, we've got a single publisher, a single receiver, that all of the messaging that's going through coherence is being funneled through these 1 or 2 threads. Right? With MessageBus, and this diagram shows specifically the RDMA implementation, but this is true of all the implementations, we now have a dynamic configurable number of threads that are handling this. Right? So we, logically speaking, have a separate channel, a separate bus to exchange messages from each service. Right? Again, this is what we're looking to do here, is be able to spread that load, be able to eliminate the pain point of having that bottleneck on the I/O threads by now being able to spread these connections, these message bus connections, now over multiple threads. So you can see here what the RDMA implementation of this would look like now is you've got client threads, or client or service threads that are exchanging messages. Those messages are going over multiple pipes to the message bus, right? We've got multiple threads that are servicing that. Message bus through Infiniband is using RDMA directly to write into, basically pass that message to the remote memory on the other side, and the message bus on the other side picks up that message, and then again has multiple pipes, multiple threads to deliver those messages to the service to be processed. Okay. And again, this is showing specifically the RDMA implementation, but to rewind a little bit, we have a TCP-based implementation, which I believe is going to be generally available in 12.1.2. Yep. It is. Okay. So most of this diagram still applies. What you would do is just substitute TCP, Ethernet, so on and so forth. Right. All right. Okay. So I've been talking a lot about the network layer and the re-architecture we did to move away from the publisher and the speaker to introducing message buses. The message bus and multiple message bus connections per service allow us to better scale the network layer, right? But what about scaling up the service threads? Right? Because I mentioned before that it's not only the network I/O threads that were becoming a bottleneck, but the service threads themselves are becoming a bottleneck, right? If we go back to that, if I go back to that first slide, on that message exchange flow, right? We had the service, we had the client thread putting the message on the wire through the I/O threads. The I/O thread on the other side would pick it up, pass it to the service thread. It would either process it itself, or it would pass it off to the worker thread to process. Then it would spool a message. That response would go back to the service thread on the other side, which would either process it itself or hand it off to a worker, so on and so forth. So, so we already kind of addressed scaling up the network tier. What about eliminating the service thread as a bottleneck? what we noticed was that some of the operations that we're doing historically that we're doing on the service thread are actually thread safe, and we can start thinking about taking a lot of those operations off of that single service thread and spreading them out to other threads, right? So if we look at some of the operations that we're doing on the service thread, doing message deserialization, so extremely expensive, but inherently thread safe, right? We've got a serialized version of the message. There's nothing contentious about that. A lot of the processing that we're doing is already inherently thread safe, right? We already have support for worker pools, things like that. The service thread's involvement in this was merely to take messages from the receiver and put it onto a queue, right? So we started to look at ways to avoid that. And again, the motivation for this is to start reducing the number of context switches, because they're quite expensive and they start really adding up. I think Mark profiled this and saw on average our context switching under a load is costing us about 15 micros for each context switch. So what we did was we noticed that by changing the transport to MessageBus, right, we've now got multiple MessageBus connections, logical connections in the member. So each service has a logical connection to each other service member it's talking to. Those connections are serviced by a pool of MessageBus threads, I/O threads, right? And the size of that pool is dynamic. We kind of tune it, and these I/O threads are the threads that we emit these MessageBus events on, right? The MessageBus events being, for example, hey, here's message arrived, right? Here's a message. What we noticed is that, again, a lot of the processing that we were previously doing on the service thread is inherently thread safe. So what we do is we're starting to borrow the I/O threads to do a lot of the processing work on, right? We can do deserialization on the I/O threads. We can, in the case where all the service thread was doing was taking a message off the queue and handing it to the worker, well, we can hand it directly to the worker on the service thread. Or we can directly process the message if it's a very simple message to process, very cheap message, for example, a backup request, right? Back this piece of data up. Okay, put it in this map here. Great, done. So we can start doing what we're calling message preprocessing, right? Doing a lot of the work that was historically done on the service thread, doing that on the I/O threads and borrowing them, if you will, from the I/O thread pool. And this gives us a single place to kind of start tuning, tuning the size of this thread pool to respond to, again, how much physical resources we have, how many cores we have to work with. Okay. So in the preprocessing picture with MessageBus, this is what the simplified flow would look like, right? We've got a client thread that's sending a request. We still block the client thread pending the logical response to this message, right? We send this request message via MessageBus to the other side. Right? The other side on the MessageBus thread, right, on the I/O thread, processes that message and sends the response. And then again, on the I/O thread, we can directly unblock the client thread. Right? So we've eliminated from this picture something like 5 or 6 context switches, right, by doing this preprocessing over MessageBus. Right? If I go back to the original picture, we had 1 context switch, 2, don't count this, 3, 4, 5, 6, 7. Right? So we eliminate a number of context switches from the flow. And this is just another way of looking at it. With the legacy datagram-based transport, we would have. This is showing kind of the receive side on the server getting, for example, a GET request or a PUT request. Right? So we read the packet on the listener thread, context switch, pass it off to the receiver thread, whose job is to deliver it to the service thread. Right? Again, context switch. Service thread would deserialize the message, pass it to a worker thread. Right? Would process the message, send the response, which is again a context switch to the publisher thread. So we've got 1, 2, 3, 4 context switches locally in handling a simple GET or PUT request. With MessageBus, we can do all of that on a single I/O thread. So we can borrow that I/O thread from the MessageBus pool, read the message. In this case, we're showing via RDMA, deliver it. Right? So we're not really delivering it to another thread, and we're just making some local changes. Deserialize it again on the I/O thread, process it directly on the I/O thread. From the I/O thread, send the response, and then write it out over RDMA without any context switching. So, to summarize, a lot of this work was motivated by the Exalogic platform, by some of the hardware improvements that, the direction of hardware improvements in the market in general, as well as the Infiniband facilities that we had to work with. But what you can see is that, we designed MessageBus to be a pluggable API. We designed MessageBus with RDMA in mind for sure, but as well TCP-based implementations. And a lot of the re-architecture we did in the product to accommodate MessageBus, as well as some of the follow-on work to reduce other bottleneck points. Certainly you're gonna get that advantage on Exalogic with the RDMA optimized transport, but you're going to see these advantages in the product in general by moving to some of the other MessageBus implementations on commodity hardware, if that's where you're on. So basically the take-home message here is that while a lot of this work was motivated by Exalogic, a lot of the fruits of what came out of it are generally applicable to the product in general. So what I want to do is kind of move on to talk about some of the storage work that we did. Before we do that, since it's a little bit of a context switch, are there any questions on the networking side of this? Yep.
Yeah, using a ring buffer there, did you use a disruptor algorithm based on that?
A disruptor algorithm?
Yeah, that Martin Thompson, he has on a site where he describes the work he's done with very fast ring buffers and pre-allocation of memory buckets and stuff like that.
So, to be honest with you, I don't know too many of the details of the implementation of that, and it's also continually evolving, right? So, the implementation in Exalogic v1 versus v2 versus the next version, it's continually evolving, and I don't directly know the implementation details of the algorithm. I know that at some point the implementation is basically, we have fairly fixed size ring buffer, and we have, the tricky part of the implementation, as I understand it, is, with RDMA, it's very easy and quick to write into remote memory. The trick is notifying somehow the remote side that there's something to be read, right? So I know that there was a lot of work put into kind of tuning the logic. There's essentially a thread on each side that's responsible for monitoring that ring buffer, right? Mm-hmm. And a lot of work is put into tuning the logic to figure out, well, how do we make this thread both respond to unsolicited writes that occurred, but not also burn a core while it's doing it. So I know there's a lot of logic and tuning that was put into that, but beyond that, I don't know too many of the implementation details behind it.
Well, you don't know if you've got multiple threads working outside the ring then, do you? You've got a single thread, or you've got multiple threads like this, isn't it?
Well, we've got a single thread monitoring the ring buffer, as I understand it, and it basically is just pulling metadata packets, right? Either receipts or message delivery metadata, and that's handed off, I believe, to multiple threads. Yep.
Actually measure the performance before and after.
Did we measure that? Yeah. So again, I'm going to hedge my answer to that a little bit and say it's continually evolving. I think what I can say is that depending, in certain circumstances, I think we've seen writes in the range of 100 microseconds, something in that range. But again, there are a lot of variables at play, right? How much load you're putting into it, what the data sizes, what the payload sizes are, so on and so forth. I think in general, and maybe Craig, we used to have a slide that spoke to this in general. I think that what we're going with.
Yeah.
He's giving me.
Well, yeah. If I heard the question today, it's what kind of performance can we quote on the Infiniband?
Yeah.
I think what we're saying is that right now where we are, for 4K network hops is 100 microseconds round trip. But as you add a lot of load, like the testing we do internally, we're going up to like a half a rack of Exalogic coherence on Exalogic that don't know whether that would be relevant to use cases or not. And at lower rates, we're seeing best case network hops at 100 microseconds.
Everett?
How do you turn it on?
So how do you turn it on? In Exalogic, an Exalogic by default, you'll get the RDMA-based implementation in the new version of Exalogic. For the TCP-based implementation, we'll add it to the docs. I think it's already, is it already available licensing-wise?
Yeah, so just to clarify that point that was raised earlier, when we went out in, I think it was 3.7.1.1, there was a little bit of confusion in the licensing doc that has since been clarified. So all versions are available on well, TMD is available on all platforms today. The reason that we didn't go out and talk about it a lot is that we're still in the process of hardening it and of making sure that it's what we recommend. So we don't recommend it as a default yet, but certainly if you want to test out with it, we're definitely interested in the results.
Yeah, so I think it's something we'll clarify in the docs, but there's a single system property you could set to turn it on, the TCP-based implementation. The RDMA-based implementation,
Obviously.
Exalogic.
Obviously. So,
There's an element called reliable transfer.
there we go. That's what I wanted to do.
Yeah.
Reliable transfer is what we're looking for.
Tangasol.reliable.transport equals
True.
Okay.
or in the override.
Reliable transfer. Now one of those is for next.
And I would regard TMD 3.7.1 as experimental. We definitely considered GA level development, a lot more testing. But I think if you wanted to play with it in some way you already have, I think certainly you would want to try to test it. If you're part of the data program, by all means, consider it a real thing and definitely
And I think in general, I mean, without making specific commitments, I think in general it would be fair to say that this is kind of the direction that we're moving towards, looking to the future, right? So I think where we're at now is, like Alex said, we're getting to the point of building that confidence to make it a default. It's not a default yet in 12.1.2, but this is kind of the direction that we're moving in towards the future.
The other question is that diagram that you had about the RDMA rewrite message bus and how everything is working. That is RDMA specific, correct?
Yep.
And do you have another one of those diagrams for people who would be on commodity hardware to explain how the TCP/IP transport works, or does it work exactly the same?
I just want to be clear which diagram you're referring to. This one here?
Yes.
Well, this is basically dissecting how the RDMA transport works. For TCP, we're just using standard TCP send and receive. But this is basically all of this, all these shenanigans essentially are to get around the fact that, like we were discussing before, with RDMA, it's very easy to write into remote memory, but notifying that process on the other side that memory's been written is the tricky part. Because again, by doing this, we're skipping the operating system, we're skipping, there's no kernel interrupts, there's nothing, right?
And this all makes sense. I was just wondering okay, this is RDMA specific, and then there are details in the other implementations of how message bus would work, and are they the same? Are they logically somewhat different? Where does the plug-in plug in?
Well, this is basically looking at a level of abstraction where with TCP this would be TCP send, and this would be TCP receive. Right?
Okay.
I mean, this is.
I understand.
Yep. So I mean, I can draw you that diagram, but the interesting part, again, the interesting part of this for TCP, right? The interesting part of this would be the changes that we made in, in the service architecture to allow for multiple message bus connections and endpoints, and again, doing the pre-processing and unloading the service thread. The transport level diagram of how the TCP-based message bus works is it's just standard TCP. It's the in that case the interesting part is the architecture changes that we made to utilize it. Yep.
The performance gains that we've been talking about.
Yep.
Based on two aspects, isn't it? RDMA implementation and the time that we save on context switch. So if we go for a TCP-based implementation where there is no RDMA, would we still have the performance gain that we're talking about?
Yeah. Well, not the 100 microseconds, right?
Sorry. So to be more precise, is the context switching a bigger save on the performance, or is the RDMA bigger?
So I think that it's hard to tease apart, is what I would say, because you've got so many different variables at play. Again, we're looking at load, we're looking at payload size, so on and so forth. I think what I can say is that we've done performance testing against the datagram transport, against the RDMA-based transport, against the TCP-based transport, and I believe in the general case we do see improvements going to TCP-based message bus over the legacy datagram-based transport. We don't see 100 microseconds, but we do see measurable noticeable improvements. And again, it comes back to there are a lot of variables, right? A lot of this work in terms of the architecture was designed to be able to scale up better, right? So as you try to scale up to bigger and bigger hardware, you're going to see more and more marginal improvement by going to TCP-based message bus over legacy datagram transport. Craig?
Yeah, just to add that, I think one other benefit that's not directly noticeable from this is that as you're trying to build really large data grids, terabyte, more than a terabyte, what you want to do is reduce the number of JVMs that have to run on every machine, or you get to a real, becomes difficult to manage that whole environment. And by breaking some of these scale-out limitations that Rob talked about, it should be able to combine with improved GC as JVMs move along. You should be able to configure larger JVMs and scale to those cores without seeing the scale-up limitations that you would see for JVMs. It's kind of a side operation.
Yes.
Just something to add to the previous question about performance. Those numbers you quoted for the 4K byte packet effectively become the transmit time plus 2 complex switches on either side. And that's what you were saying before is you're going to have likely to have 3 or 4 complex switches on either side.
Right.
So you're at least getting probably reducing the overhead by about half. At least. Even on the
Yeah, again, it's hard for me to make generalizations like that and say a half. You're certainly reducing the number of context switches. You're certainly getting a win from that. But again, to Craig's point, there's so many variables, right? It's the work is designed to allow us to scale up better, and that's where you'll see it on. But it's hard to make generalizations like that, and and we have a lot of ongoing testing and work to try to prove this out over. I mean, the number of different dimensions that we test this on, the number of different configurations, it's almost mind-boggling, right? So what we're doing again is trying to tune it and trying to make sure that we can deliver a consistent win over a general case. But I don't think that we're at the point where I can give you a specific number in the general case.
The general direction that seems to be emerging from the performance testing so far is the case of message bus running on TCP, DNP option. We do as well or better in almost every dimension, both in scale out and just raw performance. But raw performance improvement is not like double, it's like percentage points. The line is running very well, tracking and above the performance we get with our traditional DNP-based transport. And that was our goal before we could sort of stop talking about it. We wanted to do as well or better. And we do significantly better on Exalogic, which should be surprising, but that was our goal. We get significantly better performance, we get a lot of tracks. We're still trying to, the number of variables is very difficult to sort of try to summarize into a single statement simply
thing that kind of, when you move from UDP to TCP for transport model, does this impact stability and improve stability if you had virtualized storage disabled members of the cluster?
Virtualized storage disabled. I mean,
so what I've seen clusters out there where they're using virtualized clients, and they have real non-virtualized storage members, and there's a lot of trash within TCP, right? You're dropping packets because you have bad network protocols and whatever.
Yeah.
And when you remove TCP or TCP and you go to UDP or TCP/IP, it would seem that that might also benefit that model to stabilize those connections.
Well, I mean, by moving to TCP, it allows. I mean, a lot of what we built into TCMP over Datagram was to build back into, on top of Datagram, a lot of the things that you get in the TCP stack, right? So, flow control, reliable delivery, in-order delivery, guarantee, all of those things are things that we built in software on top of the Datagram stack. So you're getting those. I don't want to say for free. You're getting those
For free.
Well, it's not for free. You're paying for it somewhere, right? But you're getting them by virtue of using TCP stack, right? So, but to get to your question about stability, historically on the datagram-based transport, our notion of stability is trying to suss out, well, in a connectionless environment, how do we determine that a connection is broken, right? And we have many different methods, and we can go on forever talking about that. With the TCP-based implementation, we have a physical connection, right? A physical connection breaks, like.
No, but still, the packet-based patterns are down there. The packet is lost. The packet is lost. There's nothing you can do about it. Right? Whether it's TCP, UDP, or any other transport,
I think
packet
it's
is lost.
It's less orthogonal. I don't think it's any direct correlation.
All right. So we're running a little bit long on time. I wanted to spend a few minutes talking about the storage-based optimizations. Hello? Hello? Looks like this died. I want to spend a few minutes talking about some of the storage-based work that we did for Exalogic. We have follow-on questions on the networking side. We'll be here all day, so just find me in the hallway or something. All right. So we have a feature called Elastic Data. It was introduced in 3.7, I believe. And what we're looking at here is to start making use of some of the other physical resources that we have at our disposal, namely disk-based storage, so and Flash in particular, to start thinking about storing larger amounts of data. Right? So what we did with Elastic Data is we introduced a specialized quote-unquote backing map for the caches. A backing map is very simply the internal data structure that we keep stored cache data in. Historically, with On-Heap Storage, we store that in an on-heap data structure, a hash map, if you will. With Elastic Data, what we've done is we've introduced a specialized backing map, which is fairly complex, but you can think of it as a journal data structure that's split over a portion in RAM and a portion on disk, on flash. Right? The way we design this is we want to be able to store larger amounts of data, but we also, by using Flash or using the disk resources, but we also want to make use of the RAM that we have. So we don't want to just simply move everything off to disk, right? So we have kind of a two-tiered backing map here, right? We have a two-tiered data structure where part of the storage, part of the journal is held in RAM. Right, so the most frequently used data we can service from RAM, again in this journal data structure, but then that RAM journal is able to now overflow to disk or SSD. Right. And that overflow, that switch between, clearly needs to be transparent to the application, other than possibly latency that's observed. So just to quickly review, with a traditional on-heap storage, we've got a backing map that's held in the JVM heap. Right, so we've got your keys. And we've got your values. I've kind of cheated in the diagram here a little bit to make it readable. In actuality, we hold binary keys and binary values, but just to make this example readable, I'm showing you kind of the readable version, right? But the key here is we have a backing map that's an on-heap data structure. It's on the JVM heap. That's where we store your keys, that's where we store your values. The memory here, because it's on the JVM heap, is managed by the JVM. It's managed by the garbage collector, which means that updates, changes to this backing map create garbage, which generate GC pressure. Right? With an on-heap solution, your capacity planning, JVM tuning, all of these things start becoming extremely critical because improper capacity planning really starts leading to either pathological behaviors on the GC. If you fill up the heap too much, you're constantly going to be in full GCs, or in the worst case, into just complete out of memory. Right? With Elastic Data, what we're starting to do is to move the storage off heap, right? And when I say off heap, I'm primarily talking about the JVM heap, but I'm also talking about out of the RAM, right? So we did a couple things here. Right? One is that rather than store the keys as full copies of the serialized key, right? We still store the keys logically in memory, logically on the JVM heap, but we actually start breaking those keys up. We break them up into a radix tree structure, right? So we basically, you can think of it as a compression, right? So we basically store your keys on heap in compressed form, and then those keys are mapped to essentially a ticket into the journal, right? Basically a logical address into the journal. And that address can either be a journal that's backed in RAM or a journal that's backed in Flash, right? And there's some mechanism to basically overflow from one to the other, read through, all that sort of thing. It's completely transparent. So if you notice that now we're storing the keys in compressed form on the JVM heap, all the values are now moved off heap, right? Some of the values are stored in the RAM journal, some of them are stored in the Flash journal, right? We still have a portion of the RAM, we're still making use of that memory, but we're moving it off heap, right? What this allows us to do is it allows us to control essentially the garbage collection, right, of this memory. Right? In the on-heap scenario, right, because we don't control the memory management of this memory, right? As we generate garbage, we have a lot of high fidelity information about what's live, what's not, but we really can't feed that back into the GC, so we're really at the whim of, again, capacity planning and GC tuning. Right? With the RAM journal, we have, again, we can, because we have high fidelity information about what's live and what's not, we can directly feed that into the compaction process, basically the GC, which is now our logic, right? So we take responsibility for this large block of RAM, and we manage that memory. We manage that memory by compacting old values, or we manage that memory as we overflow. We can start overflowing to Flash. Right? One of the things that I forgot to mention, why did we choose a journaling structure? Well, again, this work was motivated by wanting to take advantage of some of the hardware resources we have at our disposal with improvements in the hardware market, specifically Flash. Right? So if you look at Flash, there's quite a difference between speeds, the latency speeds of random writes versus append writes, right? So that's why we chose a journaling structure, and with a journaling structure, basically all the writes are appends, right? So with a journal, we always write to the end, and we have some background process that goes back, and as keys are removed, we kind of compact and we garbage collect that space. Right. Couple other things. Rather than have each change written directly to disk synchronously, we batch them up. We basically hold them in memory. So there's a part of this that I didn't show you that's kind of internal. But as requests are being served and we're updating keys, so we're updating the values for a key, rather than wait for that write to synchronously go to either RAM or to Flash journal, there's an internal buffer that we hold those writes in, and we batch those writes and we write them out in large blocks. And the block size is tuned for the native device block size on Exalogic, right? Because if you look at, and I'm not sure if this is still true of the most recent Flash devices, but I think if you look at, go back a couple years and look at Flash devices, the cost of basically a block size write is free. Or not free. A block size write is a fixed cost, but a write of a smaller than block size is actually a read, update, and then write. So by by writing in block size, we're actually able to save quite a bit of latency. I mentioned before that it's a journaling style data structure, so all the writes are appended to the end, and as logical empty space becomes available, we have a compaction, a GC algorithm that basically goes through and takes up that space. So, so that's elastic data in general. We've done a fair amount of tuning, again, both in terms of performance as well as looking at our GC algorithm in terms of the application to Exalogic. Right? With Exalogic, we don't have a ton of flash at our disposal. But what I wanted to show with the next couple of slides is how, how elastic data as a storage mechanism allows you to cope with kind of borderline capacity planning issues. So this is, don't get too fixated on the numbers here, I'm just trying to show a trend. With the on-heap storage, right, what this is showing is that as you increase the data storage size, how much data you're storing relative to the heap capacity. So this is about an 80%, I think this graph was generated on 72 gigs and this is 58. So as you are approaching 60, 70, 80% of that heap, when you hit that capacity limit with heap-based storage, you fall off a cliff, right? There's kind of like this point of inflection where you start triggering and falling into really pathological GC behavior, right? Your latency shoots up, your throughput drops to the floor, right? This is 80,000 transactions per second. This is 5,000, right? So basically complete unavailability, right? 100% of GC. With elastic data, going over capacity becomes an issue of predictable degradation in performance. The scale changed here a little bit, right? But what you can see is that as you approach 90, 95% capacity, your throughput, it does drop, but we're not falling off of that cliff. So we went from 70,000 down to about 45,000. Clearly not ideal, right? We're still doing a lot of work, but in this case, a lot of the work that we're doing is RGC, right? It's not the JVM GC that we're thrashing, it's RGC, and we have a lot more fidelity and a lot more tunability in terms of managing that process, right? So the way I would look at this again is, on elastic data, this is just another view of those graphs. With the on-heap case, as you approach about 80% of heap utilization, you really fall off a cliff and just become, either completely in GC all the time or just completely run out of memory, right? The GC can't keep up. With elastic data, we're able to really, we're able to extend that out quite a bit further. And again, make capacity planning issues a performance problem rather than a stability problem. Right? With the availability of more hardware resources, more flash, more disk-based storage, clearly beyond this, this also allows you to store much, much larger volumes of data, right? But as it applies to Exalogic, within the hardware constraints that we have, the way I would look at it again is it's a mechanism that allows you to really look at that edge of your capacity planning and how that pathological behavior is going to manifest itself. And then a few pieces of kind of future direction, again, subject to that first slide I put up, so no commitments here. But moving forward, some of the things that we're focused on in terms of elastic data, we'd like to be able to do more to support queries, so moving some of the index data structures off heap. Again, looking at larger and larger and larger data sets, we want to reduce, the amount of metadata. We've moved the actual data off the heap, right, the values. We want to start looking at some of the metadata that we hold, so indexes, for example, start moving those off the heap and being able to support better query performance. Support for expiry and eviction-based elastic data caches, as well as just further tuning and optimization of kind of our GC compaction algorithm. And I think that's all I have. We're pretty over time, but we can take a few questions if there are any on elastic data.